the Quality Control Analytical Technology Group, specifically Advanced Process Control Team for Biogen. Today I'm going to be presenting a high-level overview of some of the work being done at Biogen, utilizing the Waters BioAccord system to internalize some testing that is currently being sent to CROs, as well as showing the ability to optimize some of the assays currently run on other platforms. So today I want to provide you just a general overview of what antisense oligonucleotides, or ASOs, are, and a little bit of the manufacturing process at Biogen. That will then lead into the assays we'll be talking about, including sequencing testing. We'll talk a little bit about what those tests are, the fact that they're sent to CROs, some of the challenges in terms of internalizing those assays, as well as our current platform for our multi-attribute monitoring method that provides information on assay ID, purity, and impurity for our ASO products. And the hope to actually shift to a high-resolution platform like the BioAccord to ease some of the burden on our analysts, as well as optimize our workflows further. I'll also talk a little bit about the future of this platform at Biogen. So for those of you who don't know anything about ASOs, or if you have very little background about them, they've come into the news a lot lately. Antisense oligonucleotides, you can essentially think of them as a modified version of DNA or RNA. They were discovered in the 70s and actually found to inhibit viral replication. Scientists actually tried to utilize this technology in early clinical trials, but they failed to show any significant results due to their instability in the human body and the ability of the body to actually break them down fairly quickly. So as the decades went on, scientists actually introduced a variety of modified nucleotides and/or amidites. And amidites are actually the units that actually build up the ASOs. Introduced these modified nucleotides and amidites in the 90s, as well as modified backbones. And this allowed for ASOs to really be utilized and produce clinically significant results to treat diseases such as SMA and potentially ALS and numerous other neurological and other non-neurological diseases. The image down at the bottom just kind of shows some of the minor modifications you may find within ASOs, such as the exchange of a sulfur for an oxygen. Some of these, peptide nucleic acid type backbones, and a variety of other sugar bases that can help with stability and prevent breakdown within the body quickly. ASOs actually have a variety of functions to produce those clinically significant results to treat diseases. They can range from either targeted degradation of that specific RNA. They can actually prevent translation as well, simply by binding and inhibiting a variety of proteins from interacting with the RNA and translating that into proteins. They can also help by modifying the actual splicing that occurs. So you may have a variety of types of proteins that could be formed from a single strand of RNA. And what controls that protein is actually the final sequence there after the initial transcription. So what we can do is actually target specific points within that RNA and either inhibit or push forward a specific type of splicing. So there's a lot of ways that we can go about utilizing ASOs. It seems very simple treatment, but it's actually a very complex treatment that requires a lot of development in terms of trying to identify the correct targets and making something specific enough to achieve our ultimate goal. So when we look at the pipeline within clinical trials, it's a very rich number of ASOs that are being utilized by a number of companies for a variety of treatments. We won't run through this, but I really just wanted to show you that this is a really growing area for treatments for existing diseases that already have treatments to diseases that we may not have been able to treat until now. So a little bit of information about Biogen's current process for ASOs, and really when you look at this, Biogen's current process may not differ a whole lot from a number of other companies' process in terms of synthesis, purification, and that final fill and finish. But generally speaking, you'll have a solid state synthesis. There is the potential for a liquid phase synthesis, but Biogen specifically utilizes a solid state synthesis, followed up by a deprotection step after the synthesis of the oligonucleotide, and ammonialysis or a cleavage from that solid phase support. Afterwards, our specific process utilizes a capture step and an initial purification through chromatography. A deprotection step happens afterwards to remove our DMT group, followed by a polishing step to remove any number of impurities that may have appeared during that deprotection step, as well as trying to further decrease some impurities that may have been present during the synthesis. And then afterwards, moving down, you will notice that this is very similar to anything from large molecules to potentially even small molecules. So you'll see UFDF steps, liquid drug substance storage, all the way over to formulation, sterile filtering, and fill, as well as visual inspection. So it seems to be a very standard actual process for synthesis and purification. But there's been a lot of work, obviously, into optimizing these workflows, not just for ASOs in general, but for every single molecule in our pipeline. So when we look at this, you can kind of break it down even further and simplify it more, just with some images to give you an idea. There are multiple coupling steps in that first step. For synthesis, you have repeating additions of different monomers of any of those amidites that you're adding to build that sequence, followed by either an oxidation or a sulfurization step for that backbone. You then repeat that over and over again before you then cleave it through the ammonialysis, as was stated before. We then have that LC purification and that deprotection step that occurs in a very acidic environment over a period of potentially 3 to 4 hours or longer, depending on the sequence. And then, of course, the final purification, UFDF. So there are a number of places here where we may have a variety of impurities that appear that we need to keep track of and or characterize. So Biogen specifically needs to understand the sequence that's produced. So are we actually producing the sequence of interest, as well as the impurities that are created during this synthetic process? And then during our purification, we want to understand where we're removing those through mass spec as well. And then finally quantifying those impurities and providing, of course, a final purity and concentration. So our current LCMS platform that we utilize, one, for sequencing, the platform is effectively the platform that the CRO utilizes, which is essentially any high-resolution LCMS. Unfortunately for Biogen, there's a significant turnaround time associated with this, from when samples are sent to when they can actually return the reviewed results, so we can move forward from initial synthesis to start our purification. Typically, ASO analysis, specifically LCMS, requires an ion pairing reverse phase mobile phases, which can present a number of problems for a CRO environment, which may utilize an instrumentation for a variety of projects. Ion pairing is a known contaminant of systems and requires a significant amount of cleaning and requires a lot of goodwill on both sides to ensure that the system will not be fouled and prevent the CROs from performing their work for other clients. Unfortunately, this does begin to present an issue. And for us, it would be in our best interest to really internalize this testing to not only control the turnaround time, but to also remove any of those extra costs that may start to pile up due to the time spent by CROs for cleaning their instruments. And one of the big things here is we actually already have a method that's built in that actively monitors the sequence in real time using a variety of other instrumentation within the synthetic process. And this is a backup that requires a lot of contracts and validation up front for a process that may not actually be used. So just looking at that, we internalizing this allows us to save money, while also saving time. Now we look at the multi-attribute monitoring method, which provides information on ID, assay impurity, and purity. We utilize an Agilent single quad platform. Unfortunately, this system, due to the inability to provide high resolution data and some of the ambiguity and data analysis, requires a very extensive amount of analyst training, a variety of very long, complicated sample sets, and some difficulty in identifying and even quantifying some very closely related species. So, looking at this, after being onboarded at Biogen and understanding further some of the strain that's occurring within our QC labs and trying to get this turnaround time knocked down as well as time savings, and to allow for our analysts to not be burdened so much by data analysis, I started evaluating a number of systems from a variety of different vendors. It really came down to the Waters BioAccord system. The intent for this was really to try to reduce our operational expenses and our QC hours spent on validation activities, and the sheer amount of time on data analysis. Looking at high resolution, this provides a variety of benefits to us, specifically around removing ambiguity of such things as impurities, and gives the analyst much more confidence in what they're looking at. When we look at the BioAccord system and specifically Unify, a lot of this time savings can be seen when utilizing things such as a screening workflow. We already know from our sheer amount of characterization work done on these products what we're looking for. So what we can actually do is build a variety of libraries and actually just compare those libraries to the data that we receive through the mass spec. Leveraging that with those workflows really allows us to streamline our data analysis all the way to the very end in terms of creating a C of A to provide that final ID, that final purity, and understanding what impurities may be present in our sample. And that's really why I started pushing forward with the Waters BioAccord high resolution system. So starting off, I mentioned sequencing. Typically, sequencing, for those of you who may do this with peptides, seems to be at this point in time a very straightforward process. There are a variety of software packages out there that can easily interpret CID data, as well as a number of other types of data from different mass spectrometers to give you a very simple way of sequencing that main product. Unfortunately, as shown below, oligonucleotides actually have a very complex fragmentation pattern, which makes simple data analysis in a compliant environment very difficult. Especially including the fact that there are multiple colloid impurities, which may then further create complications within those fragmentation patterns. So really with ASO sequencing, this is simplified by simply using those early termination sequences, which typically appear in that crude material. So during the synthetic process, and this is very typical even of peptides, you will get early termination sequences where not every bit of material is reacted with each monomer that's introduced. So even at 99% efficiency for that reaction, you will slowly build those early termination sequences. But what we can do is leverage those and separate them by LC and then identify them through mass spec. And this is what is currently sent to CROs and what we hope to actually internalize at Biogen. So when we look at this, not only did we have, once again, the ion pairing problem at the CRO, it presented an opportunity for us to slowly try to move away from that by introducing the Hillock separation. This Hillock separation utilized a simple water, acetonitrile, and ammonium acetate mobile phases on a Hillock column with detection at 260 nanometers and some of the RDA parameters for the BioAccord below. So a very simple method just to get some very crude separation between our early termination sequences that determine our sequence of our full length product or our FLP. So looking at this, the what we require is very simple. We need to have fairly good mass accuracy. And as you see in the second column highlighted in red, of each one of the mass errors are roughly below 10. Majority of them even below almost 5 ppm. It's a very good ppm. That's what we need. We need to actually have confidence in the identification of these species. What we also require is an increasing retention time. So essentially, do we what for each short sequence? Do we actually see? Do we actually identify it through mass, and then do we see it increasing in retention time with each addition of a monomer? And we do. So it's a very simple process. And what we can actually do is we know what we expect in terms of these early termination sequences. So we can utilize a screening workflow as opposed to something like an intact mass workflow and really streamline our identification as well as our mass extractions, XICs, to give a really nice picture of what we're expecting in terms of a sequence. So what would look like in a very crude way is below. We utilizing the screen workflow and then the known retention times, we would actually have the system screen for those known masses and then pull out an XIC. We can then lay those out and show that yes, we've identified every single early termination sequence. We can show the actual mass errors for each one, and then lay those out in a very nice C of A. So what I'm just simply providing now is really what the analysts are looking for in the data. So you'll see all the XICs overlaid together, and then the identification above that, such from N minus 17, which denotes the number of missing monomers, all the way to N. What we also look for, besides that, is we want to make sure that the isotopic distribution is what we expect. And this is just to provide some information showing the performance of the system. So when we look at what we would expect for a high resolution system, what we do see is the ability to easily separate out these isotopes all the way from very low masses, which is on the right, up to the high masses, which this particular species is around 7,000 Daltons or so. So we get very good separation, and the system is easily able to discern between each one of those isotopes to allow us to get not only the high resolution, but that high mass accuracy that we need to confidently identify these species. So when we really look at it, the BioRecorder really provided a very simple process to transfer these sequencing methods. It was one day of work, and specifically trying to leverage that system with the Hillock method to move away from ion pairing really allowed us to not only streamline these workflows internally, but utilize a more green chemistry as well, and decrease the waste of our mobile phase additives. What we're doing now is really trying to work with QC and to design a simple report for release as well. The current reports, of course, on our end, when working with a CRO, there's very little that we can do on our end to change the types of C of A's they can release. We can modify them slightly, but what we can do when we internalize this is really control every aspect of that and provide a very nice, clean, simple C of A to send off to continue the process. And when we look at leveraging the BioRecorder, it's very minimal work for an immediate savings. Every single compound that was ran required 2 to 3 initial runs to optimize the separation. And then from there, the processing method was very simple to produce. And that upfront time, there will be more time in the beginning to actually set the method up. But once it's actually set up from there, it's a very simple, streamlined process that we can continue on day to day. And one big part of this, especially when we try to justify internalizing and moving to a new platform, is the fact that the ROI calculated based off of the number of molecules that we have in the pipeline and what we expect these CROs to run based off of validations and the cost of those, we'll see an ROI of about 1 to 2 years on this system from internalizing. And what we really like to see is the fact that this ROI will of course, it'll be much faster with the addition of more assays. So this is very successful, very great initial run and evaluation of the system. We're very excited to see how easy it was to actually implement these workflows. Now, given the fact that the sequencing aspect of this was very easy, sequencing by early termination is fairly easy. we really needed to see how the system fared in a more complex method, and that's where the multi-attribute monitoring method came in. This is a very complex data analysis and can take months to learn to become very efficient to understand what you're looking at. And that's really what we wanted to move away from. We want analysts to be able to come in and start running this system within weeks, not months. As well as removing some of this subjective data interpretation. A lot of this subjectivity comes in from utilizing nominal mass systems, and we see benefit in leveraging this high mass resolution to remove that ambiguity, to remove the interpretation from the analyst and put it more into the hands of the system. So looking at this, we do have a novel Hillock method that is currently in the works, but just to make things simple, we decided to utilize the ion pairing method that's previously been published by Ionis, one of our ASO partners. And this utilizes tributyl ammonium acetate, as well as water, acetonitrile, and a chelating agent to try to remove any other salts that may be in the system due to the sample or just from the mobile phases themselves. This is a very strong ion pairing agent, also very low in solubility. There's a very large learning curve in terms of simply creating the mobile phases themselves. So not only do we have a complex data analysis, we've then looked at even a very complex system setup from just creating the mobile phases. And these mobile phases don't last very long. As soon as you open the ion pairing agent, the clock starts. You have about a week for that ion pairing agent before you have to toss it, because it does start to slowly degrade through oxidation and a variety of other means. And then with that, your bulk mobile phase will actually start to degrade fairly quickly as well. So we are trying to move away from that, but just for the sake of evaluating the system, we stuck with the ion pairing method. We have a variety of methods we utilize. Essentially, the platform we use is a C18 BEH column. There has been a long method that's been developed, and you'll see that with a chromatogram. We developed this long method after acquiring the quote-unquote shorter method from Ionis, and this allowed us to pull apart a variety of the impurities and quantify them through UV as opposed to mass spec to simplify the data analysis. This also requires a calibration curve, UV and MS calibration curve, to be created from a working standard solution. This, of course, is a previously characterized standard for each and every one of the ASO products that we have in the pipeline. And this also currently requires multiple MS methods. So due to the ion pairing that's present, the tributyl ammonium acetate, as well as the chelating agents and the metal adducts that are naturally found in mobile phases and within your LC system, we require multiple methods to actually discern what are adducts and what could be actually co-eluting impurities. So this requires multiple methods to be run, and we just call them a harsh and a soft method. And this allows us to look back and forth between the data and identify, is this a real impurity or is this simply an adduct that is co-eluting underneath that main peak? So when we look at a standard chromatogram, you can see it doesn't look very complex. These are fairly clean samples, but there are a variety of species that we do need to separate and actually quantify. So as we zoom in, and you'll see on the right, you have a variety of early eluting impurities. And these could be anything from, once again, the short MERS or the early termination sequences or any other variety of impurities due to the synthetic process or just from sample handling period. You'll have the N-1, which this is utilizing the long method, requires a very shallow gradient to pull apart that single missing monomer that exists there, that N-1. We also have an N+1. But underneath that main peak, we do have a variety of other co-eluting species that are very difficult to separate, and that's why we require a mass spec to perform that final layer of quantification that we need. So looking at the left, you'll see a very standard mass extraction for any one of our products when we run LCMS on them utilizing this method. What you'll see is that main peak centered about around 1780 AMU, and then we have plus or minus 150 AMU on either side. And typically, this is where you will see the impurities within your mass extractions. You typically won't see them anywhere else within that mass extraction. So it does make data analysis a little simpler. But when we zoom in, you'll see this is where the complexity really starts to kick in. You may not initially on first glance be able to tell which of those is an adduct and which of those may be an impurity. Luckily, anything that is less than the main product, we can assume that is going to be an impurity. It could be anything from an oxidation event to a loss of an individual monomer. It could be an actual abasic species. So those are very simple to identify, but the heavier species becomes much more difficult to identify in terms of if it's an impurity or not. And typically what analysts would have to do is actually run multiple methods and then looking at the harsh data, draw a line at 0.2% of the total intensity, and then compare which ions fall below that line between the soft and the harsh method. And this allows them to essentially understand which ones are adducts and which ones are colluted impurities. Unfortunately, with that, when you're utilizing this harsh method, you are imparting energy onto the system. So even though we may be confident that these may be adducts, at the end of the day, we may also be destroying real impurities through these harsh adducts through in-source degradation. So it would be ideal to remove that. And really, this is what the system allowed us to do. It allows us to acquire high mass accuracy, high resolution data, and since we know from the sheer amount of characterization that work that has been done, we understand what adducts we should be looking for. We can simply add those into our workflows, and that's something we're working on now. Simply add those adducts into our screening workflows and pick those out individually and not report those. So it really simplifies that data analysis even further. So this slide really is just to kind of illustrate why it is so difficult and why we do need to utilize an MS system and where the BioAccord really will come into play. You'll see in the black trace there, that is our full length product, our FLP. That's our main product of interest. You'll see every other trace in there. Those are just 4 impurities out of a variety of that could appear. Those four impurities can take analysts upwards of a week to identify and then put into an Excel sheet, have that data reviewed, and then provide a final purity and then a list of impurities. So it's a very complex data analysis that BioAccord has really kind of shown to provide some benefit in terms of moving away from a lot of that manual interpretation. But looking at this, it will still require a UV and MS portion in terms of a UV curve and an MS curve. But what we really have been able to do is streamline this analysis and have XICs that are automatically pulled out, automatically integrated, and we can utilize all of that data to easily calculate out our final purities and impurities that we expect. Without having to go to a non-compliant method such as an Excel sheet. And I won't show that data here, though. It can be very complex, and we could spend an entire day looking over that. But utilizing those screening workflows has really shown benefit in terms of streamlining this assay very easily. And this slide is just simply wanting to show the general performance of the system. On the left, we have a UV linear curve, of course, up R squared of 0.9999, which is great. And the bigger part is looking at the MS curve, which shows an R squared of 0.999, which is really phenomenal when you think of on our end how much sample we're loading, up to 2.5 micrograms of sample. So we're really overloading that column, as well as being able to still see those impurities with that sheer amount of signal that's coming through that mass spec. So the system performs very, very well. And just having this ability to even perform these simple data analyses within a compliant environment provides a lot more benefit to our analysts, as opposed to them trying to pull that data out and actually put it into an Excel sheet. So looking at this, our initial results are really quite promising. There's still a lot of work that has to be done, but what we've seen is leveraging screening workflows within Unify, the ability to build these custom libraries really allows us to minimize a lot of that manual data interpretation. Moving to this high resolution platform also minimizes the number of methods we have to run. We can finally start to move away from these two method approaches, known as the harsh and soft methods, with our nominal mass instruments, to really start saving time and get these results out faster. We can also potentially start to identify maybe new, low-level species due to the sensitivity of the system, as well as the ability to start separating out these convoluted masses that may be affected by that coelution, as well as those that may be isotopically similar. And a little bit of information there. We actually not only leveraging this system, but leveraging new chemistry as well. Specifically, our helix separation has shown the ability to start to see some of these new, potentially very low level impurities. Which is very exciting. This may not be something that we would have seen without this initial work with that BioAccord. And then utilizing these very well, I don't want to say very, but relatively simple custom calculations for our final purity analysis within this compliance system can really start driving these methods. They can start pushing them through a lot faster. We don't need to have as much data review, because we won't have to go through and make sure that that data was transferred correctly from the system to an Excel sheet. Everything will be handled within Unify. We have confidence that that data remains, unmodified and remains true to what it is within the actual method itself. So looking at the future of this, the next steps, we have a variety of exciting places we'd like to take this system. But of course, early data shows that the system does perform how we expect it to. There is, of course, still a lot of work to go. It's not, we can't simply change from one platform to another one overnight. So we still have to show that the system will perform robustly day to day. And that is something I'm working on now, is essentially putting it through its paces, running the system multiple times, day after day after day, for weeks on end, and really seeing how long and how hard we can beat the system up. What we do hope to do, though, is during these next few validations that may come up for new products in our pipeline, is really start using those same samples and compare the data between systems to see how well they compare to one another, and if we can be confident in the data, that the data is going to be consistent from one to another. What we'd also like to see, and what we're hoping to do, is actually begin working on the Patrol RDA combination as opposed to the standard UPLC. We hope to be able to leverage the Patrol system, the ability to pull online samples and actually monitor these impurities during a reaction for the deep protection, to understand our process better and understand what impurities may or may not be appearing, and if we're removing them and if they could be appearing again, just to get a much clearer view of that reaction. And when we may see, the ability to utilize this type of system and a variety of other parts of our ASO pipeline, or even different modalities that we have within Biogen. We're also looking at adding a system for our raw materials testing as well, for our amidite starting material. So understanding what impurities we start off with and how that may affect our product quality down the line. So there's a lot of exciting work to go. So thanks for listening. I hope I was able to provide some more information, some things you may not have known before, and some confidence in the system. This is a very exciting time, at least for us in Biogen, and we hope to be able to leverage the BioAccord not only in ASOs, but once again in a variety of other aspects of our business. Thanks.